Hello. Yeah, Dr. Krishna, am I audible? Hello.
Yes, sir.
And
You
my and my
are audible, sir.
okay, thank you. And my screen is visible. I think my PPT is visible to you.
Yes, sir. PPT is visible, sir.
Okay. Let's wait for maybe 3 to 4 minutes because I think today I can see only you are in the meeting. So maybe we can wait for 3 to 4 minutes more.
Yes, sir. We shall wait for 5 more minutes, sir.
Yeah.
Okay,
So
sir.
I think you have received the link for our previous classes, I think. Have you
Yes, sir.
received the
I have
links?
attended the previous class.
No. I am asking that is NPTEL team has shared the link for like my recordings and my these PPTs of previous lessons, live classes. Have you
Yes,
received those links or not?
our previous videos are available, sir. YouTube videos we have got.
Okay. Thank you. Yeah. I am
Okay,
asking
sir.
that. Yeah. Thank you. So I think now you have received a Excel file, I think. So in that Excel file, there will be link for every week, and there will be a common link for the Google Drive on which you can find the PPTs.
Okay, sir.
Yeah, okay.
Okay, sir.
Dr. Krishna, you are in which college? I think I forgot you told in first class, I think. You are in which college?
In a Ragu Engineering College, sir.
Okay. Where?
It is in Visakhapatnam, sir. Andhra
Visakhapatnam.
Pradesh.
Okay. Nice.
Yes, sir.
Yeah.
Your session is very useful for us, sir. We have solved some problems in assignment 1 and 2, sir.
Oh, nice. Thank you. Yeah, that's why we are
Similar,
NP and yeah.
similar problems we have got, sir. We have solved.
Yeah, okay, nice. Yeah. That's why NPTEL has organized these live sessions. So in this we can interact and we can discuss some questions. So because you know that discussion is a very good for studying actually. Because if you are studying alone or maybe because you will not get some doubts. But when we are discussing, so suppose there are 5 to 10 person are there, so they will so there will be different doubts will be there. So every
Yes,
doubt
sir.
maybe is a good concept.
Yes, sir.
Yeah. So discussion is a very good thing to study actually. So yeah.
The good part is, sir, along with the problem, you are discussing theory also. That is
Yeah.
the good thing which we like.
Yeah. Thank you.
Okay, sir.
So I think 5 minutes is over now. So I think we should start with our session. So okay. So good evening everyone. My name is Amit Kumar Sharma, and today we are covering live session 3, as you all aware, and maybe for new those maybe who will be viewing the session online on YouTube, or maybe those who are first time joining the session. So every Friday we are having a live session of previous week course content. So in these live session we discuss some sample problems, and in this so these problems will be very helpful to you in solving your assignments, and in that way we are discussing every week's course content. As of now we have covered 2 weeks, so this is week 3 live session, and the course is energy conservation and waste heat recovery from Professor Pratap. K.R. Das and Professor A. Bhattacharya from IIT Kharagpur. And I am the course TA, Amit Kumar Sharma. So today we will cover live session week 3. And one important information that the recording of this class and the PPT that I am going to use here in this class will be shared to you from the NPTEL team. So maybe you can download the PPT and you can because in the PPT there will be some sample question, extra sample question will be there. So you can try those question at your home and you can also see the videos. So okay, let's begin the session. So basically, in week 3 classes, we have covered the Rankine cycle with different configuration like reheating, regeneration, and we have seen what is the changes in efficiency. Okay, so we have covered different parts of Rankine cycle with different modification in week 3. So today we are going to discuss some sample problems on that. So this is the basic Rankine cycle with reheating. So basically here you can see a boiler, a high pressure turbine, a low pressure turbine. So basically in reheating, you can see from the TS diagram that the some part of the steam, you can see we are taking from, the steam from the high pressure turbine is going through the boiler and then it's going to the low pressure turbine. So in this way, you can see from 1 to 2, the high pressure turbine is developing work. From 2 to 3, we again reheating the steam and then again we are producing work from the low pressure turbine. So in this way, we are doing reheating at high temperature. So initially, for we are going from the lowest temperature, but in reheating, in between at some pressure, we are again reheating the steam and producing the work. So it is having some benefit on efficiency and also for equipment, because suppose if you are coming directly down, then you will be somewhere here. And in this region, you can see there will be more part of water. So this is not good for the compressor and all. So you should be in near such a saturation region because it will be good for the equipments also. So in this way, so reheating is having benefit on efficiency and for the parts life. So let's come with some numericals. Okay. So the first one is choose the correct option regarding the combined cycle for the maximum efficiency. So we have to choose the correct options regarding the maximum efficiency. Yeah. So take 2 minutes and come with a good reasoning for your answer. So the first option is the heat rejected by the topping cycle is the heat supplied to the bottoming cycle. The heat rejected by bottoming cycle is the heat supplied to the topping cycle. More work is done by topping cycle. More work is done by the bottoming cycle. Maybe you can link up with the answer.
Option C, sir.
Option C. Okay. Okay. We will come to discussion. Yeah. Just wait for a moment. So the answer of this question is based on our, you can see the title of the course. What is the title of the course? You can link to that actually. Because our main theme of this course, what is our main theme of this course? What we are learning here. That is the answer of this question. You can try to link that. As the question is saying, choose the correct statement, correct option regarding the combined cycle for the maximum efficiency. So what are the ways to increase the efficiency? What is the basic meaning of efficiency? Anyone? What is the basic meaning of efficiency?
Output upon input.
Yeah. So the very basic definition of efficiency is output upon input. So it says that we have to increase our output with the input. So if I want to increase my efficiency, so either I can increase my output, then my efficiency will increase, or I can decrease my input, then my efficiency will increase. So we are having two options. Either we can increase our output, or either we can decrease our input, or we can do both. Then it's a good thing. Okay. So basically efficiency is saying that how much of output we are getting from our input. Okay. So we have to maximize efficiency. It means that we have to increase the output work and we have to decrease the input. So anyone want to answer? Anyone else have any options? We are having one answer as option C. Anyone else having any option in their mind? Please let me know. Please let know the class.
A, sir.
Option A. Okay. So we are having two answers, A and C. Okay. So let's come with the first answer, C. So please explain your reasoning for answer C. What is your reasoning for answer C?
Sir, the more work done by topping cycle means, sir, the main turbine is there, na? Main turbine
Okay.
is the high pressure and high temperature.
Okay.
So getting the more work done from the topping in the main
But
HP turbine.
okay, so if you are saying that there should be more work than the topping cycle. Okay, so topping
Yeah.
cycle I think is the main cycle. Suppose these are cycle 1 and this cycle 2. Just a simple diagram. Okay. So 1 is the topping cycle, 2 is the bottoming cycle. So you are saying that there should be more work done in the topping cycle. So there should be more work done in topping cycle. Okay. So, but if there is more work done, you are getting more work done in topping cycle, then it's obvious that because the topping cycle is having some efficiencies. Okay. So for more output, you have to increase the input. Okay. Because to increase the efficiency, what are you doing? You are inserting a bottoming cycle. Okay. So you are saying that you are increasing the more work done in the topping cycle. So it means that you have to supply more input then. Okay, you have to supply more input, then only you can getting the more work done, because work is the high grade energy. Okay, and from topping cycle you want more work, then there should be more input also. So I think this option is not correct. Anyone else? Okay, now come to option A. Yeah, please explain your reasoning why the option B or D is wrong, because we have discussed about option C already. So yeah, who is saying option A? Please explain your reasoning behind B and C, why they are wrong. B and D.
Sir, yes,
Yeah.
sir. My name is Prashant, sir. Actually, what happened in option A, we are receiving the whatever input in first one cycle, complete cycle, which remain a constant throughout the cycle. And for second bottoming cycle, though no separate input is required, whatever is rejected from one when stopping cycle is being supplied to second. So there is no input for second cycle. So in this case, we are only minimizing our input, so getting a maximum work. So though there are two cycles, but input is coming in first cycle, that is a topping cycle, and for second there is no extra input. Whatever getting is from a rejected it. So
Yeah.
in that way, I think A may be right answer.
Yeah, A is the right answer. Your answer is very correct, but you forget to mention the main thing actually. This is called waste heat recovery. You have explained everything,
Yes, sir.
but the word waste heat you
Yes,
forgot to mention.
actually, I
Yeah,
forgot. I forgot, sir.
yeah, yeah. So that is our this class is about. Okay, this is our subject. This is our course that we are maximize our efficiency using waste heat recovery. Okay, so what we are doing here, the topping cycle is having some input, is producing some work, but it is having some waste heat. Okay, so what we are doing, we are using this waste heat. So by using this waste heat, we are putting a bottoming cycle. So that bottoming cycle will use the heat of the exhaust gases, or you can say any exhaust stream from the topping cycle, and use that heat to produce some work in the bottoming cycle. So in this way, we are doing waste heat recovery because, as you said, for bottoming cycle, there is no separate input. Input is same. Our input is same here in this combined cycle. But what is happening here, when we are using the waste heat of cycle 1, then from that waste heat we are putting in another cycle 2. So that cycle 2 is producing some work. So what we are doing, we are increasing our output. So as I told you earlier, we can increase our efficiency in two ways. Either we can increase our output, or we can decrease our input, or we can do both. So what we are doing here, we are keeping the input same, but we are increasing our output by combining two cycles. Okay. So in this way, the correct option will be option A, because the heat rejected by the topping cycle is the heat supplied to the bottoming cycle. Okay, what is the option B? So option A is correct. The heat rejected by the bottoming cycle is heat supplied to topping cycle. It's totally wrong, because the bottoming cycle is totally dependent on the topping cycle. And what is option D? More work is done by the bottoming cycle. So as you know that in bottoming cycle, we are not giving any input. Okay, so the work output from the bottoming cycle is limited. We cannot control that. We can control the input waste heat from topping cycle. So this option we cannot say. Okay, because it depend on the topping cycle. How much heat is going to be rejected in topping cycle, that heat only decide the work output from bottoming cycle. So because if we are using a bottoming cycle, and if we are getting any work input, that is our bonus. Because suppose if there is no bottoming cycle, then you are having only one cycle, single cycle. So you are giving the same input. But if you are putting combined cycle, then the any amount of work, suppose 5%, 10% is coming, that is your bonus. So there is no question about more work from bottoming cycle. We can control that. That's why we cannot say about it. So only option correct will be option A. Any doubt? Okay. Let's come to the question number 2. So we are having a TS diagram. The figure shown below is the TS diagram of a Rankine cycle. Choose the correct option for thermal efficiency of cycle. Neglect pump work. Yeah, very basic question. So you have to answer what is the thermal efficiency of cycle. We have given the states 1, 2, 3, 4, 5, 6, 1.
Option C.
Option C. Okay, we have an answer. Let's wait for another 1 minute. Meanwhile, you can try to figure out the reasoning for other options and what is the reasoning behind this answer. We will discuss it.
Sir, can you explain previous problem? I have some doubt.
Yeah, maybe after this, we can go to the previous problem. Yeah. Let us discuss this. Then we can again go to the previous one. I think if you know the states about like points, if you know the basic of Rankine cycles, if you try to remember the class notes, then maybe you can answer this. So, what is the 1 to 2? What is 1 to 2 representing? Anyone want to tell? What the process 1 to 2
1
is
to
representing?
work done, sir.
Work done. Okay. And what is 2 to 3 representing?
2 is a condenser heat
The isothermal process, sir.
reaction.
Yeah, isothermal is fine. Condenser actually, yeah. So yeah, basically
Yeah.
we are converting the vapor to liquid. Okay. So it's basically, what is this? It's heat addition or heat rejection? If we are converting the vapor to liquid at same temperature, what we are doing?
Cooling, sir.
So cooling mean, if you are say cooling, then cooling mean that temperature should be dropped. But temperature, you can see the TS diagram. T2 equals to T3. So anyone want to tell me how the process 2 to 3 is heat rejection process? The temperature is same.
Sir, because this is vapor is converted to water.
Okay. So what is happening
Okay,
here?
that's is even the heat exchange from the
Heat rejection, sir.
rejection, sir. Heat rejection is there because this
Okay.
point 2 to 3, 2 is the vapor phase. Okay,
Okay.
and they
Okay.
release the latent heat through
Okay.
the condenser. So this
Yeah.
is cooling. So that goes into water, converted to water.
So I was waiting for this point, latent heat. Yeah. So we are the vapor is losing its latent heat of vaporization from 2 to 3 and converting to water. So this latent heat is important. So the temperature will remain same. It is required for phase change from vapor to liquid or liquid to vapor. Okay, this is a very important point. Okay. So this is heat rejection. So then 3 to 1, because we have given the neglect pump work. So this 3 to 4 is basically a pump work, but we have to neglect it. Then what is 3 to 1 is representing? 3 to 1 representing, what is representing? What is
Pardon, sir?
process 3 to 1? What is the process 3 to 1 representing? 3, 4,
Heat,
5,
heat
6,
addition
1.
is a heat
Yeah.
addition boilers.
Yeah, it's basically heat addition. So this completely because we have given that neglect pump work. That's why we are considering complete process from 3 to 1. Otherwise, we have to consider 4 to 1. If you have given that you cannot neglect the pump work, then we have to consider H4 process 4 to 1. But we have given neglect, then we can consider from point 3. Okay, for
Sir, one doubt, sir.
yeah.
Sir, when we are neglecting pump work, then 3 to 4 should not be there, na? So how we can consider 3 is there?
Actually, the pump work is very small here. So the enthalpy difference between H3 to H4 is neglect. Actually, maybe 3 to 4 kilojoule, 5 kilojoule, 10 kilojoule per kg. So that enthalpy difference is very small. So that will not affect your efficiency very much. But for the ease of calculation, because if you don't know the enthalpy, because you can see the 0.4 in subcooling region point. Okay. So, but the 0.3 is on saturation point. So you can easily get the enthalpy. Okay. So for the ease of calculation only, we are considering it. But in actual, it should be H4. But in actual, it should be 0.4 only. But it is given in your question, neglect pump work. And there is no option also. That's why if there is option with H4, then you have to consider H4 only. Because sometimes we have to see the options also. what are options we are having? So you can go from the options actually. So the efficiency will be the output upon input. So output is the work done from the turbine and the input will be the heat addition. So output will be enthalpy of 0.1 to 2, H1 minus H2. So see the option with H1 minus H2. In option A, we are having H1 minus H2 and option C, option D. So maybe option B is directly wrong because H2 minus H1 no, because enthalpy of this is more as compared to this. Okay. So H1 minus H2. So the answer could be A, C and D. Now see the input. Input should be H1 minus H4. But no, we have no option of H1 to H4. So we have given neglect pump work. So maybe we can consider H3 equals to H4. Okay. So replace H4 with H3. So C option with H1 equals to H3. Yeah, there is option C. H1 minus H3. Okay. So the correct option will be
Okay.
option C. Any doubt?
No,
I
sir.
think no doubt. Let's come to question number 1. So what is your doubt? Yeah, please.
Sir, my doubt is if the topping cycle is a high pressure and high
Okay.
temperature,
Okay.
okay, and convert
Okay.
with the low pressure, that is the vacuum pressure and low temperature. So they produce more work. H1 minus H2 is
Surya, I am not getting your question. What is the question? You are
sir,
saying
this
that?
is this is HP turbine. Consider as HP turbine is there.
Okay. Okay.
This is the high pressure turbine and the
Okay.
high temperature turbine also. So
Okay.
if you convert with that H1 minus H2, H2 is the vacuum pressure. So they
Okay.
produce more work.
Okay.
If
No,
they
no.
produce
Okay.
more work,
Yeah, yeah.
efficiency is more.
Yeah, yeah. You are, yeah, but I think you have to, if you are producing more
Because
work in topping cycle,
because
yeah, yeah,
most of the power plant using this thing only,
yeah,
not
yeah.
using this thing.
Let me clear. As I already said, efficiency is output upon input. Okay. So you can increase the efficiency, either you increase the output or decrease the input. So I think you are referring to option number C. More work is done by topping cycle. Yeah. If you produce more work in any topping bottoming cycle, efficiency will increase for sure. But you are saying is correct. Okay, we can produce more work in topping cycle also, but you have to see the question. What is the question is asking to you? The question is regarding. It's clearly mentioned regarding the combined cycle. So
Okay.
first of all, you have to limit your thoughts to the combined cycle only. Now you have to think that you are having a combined cycle. Now for that combined cycle, you have to increase the maximum efficiency. Then what can you do? So the best option in combined cycle is to use the rejected heat of topping cycle to heat supply to the bottoming cycle. Suppose if you are producing, let me go with your option. If you are producing more work in topping cycle, yeah, it's fine. But still there is some heat in the topping cycle that can be used to produce further more work in bottoming cycle. So that is the question is asking about combined cycle. It's not about only the topping cycle, it's about the combined cycle. So to increase the efficiency of combined cycle, you have to utilize your waste heat. You have to recover the waste heat in bottoming cycle. That's is the only way to maximize the efficiency of combined cycle. Okay.
Okay, sir.
Yeah. Okay. So in this question, answer is C. Okay. So question number 3. Choose the correct statement or statements related to the Rankine cycle. So we have given 5 statements. We have to select the correct one. The first is irreversibility causes an increase in pump work. Second is irreversibility causes a decrease in turbine work. The pinch point puts a restriction on the highest achievable temperature. The thermal temperature difference points put a restriction on the lowest achievable temperature. Irreversibility does not affect the Rankine cycle. So take 2 minutes. We will discuss it.
सर 1 और 2 तो राइट है
Okay.
बी सर बी ओके
B. Okay, let's see. Please try to recall the reasoning behind every option. Okay, if that's right, you should have reasoning for right, and if that is wrong, you should have reasoning for the why the answer is wrong. Is anyone new today in the class? Is anyone attending the first time or second time?
Yes, sir.
Yes, sir. I am attending first time.
Yeah. Okay. Okay. Please introduce. Like why?
Sir, my name
what are
is-
you? Yeah. Okay.
Yes, sir. My name is Ritika.
Yeah.
I am pursuing my MTech in DAVV College, Indore, in Executive Energy Management.
Oh, nice. Nice.
First, yes,
So, what is the reason
Ritika, you are
behind
first year?
to taking this course?
yes, sir. Yes, sir. I'm a first. Sir, I'm working in Bureau of Energy Efficiency.
Okay. Okay.
Okay.
Okay. Nice.
नहीं,
Yes,
I
sir.
am the second year
You want to
student of
know
the
how to
DAV.
increase efficiencies of cycles. Okay. Yeah.
Yes, sir.
Yeah.
Thank you, sir.
Anyone else? Yeah. Thank you. I think one more guy was there. Please introduce yourself.
Yes, sir. My classmate is Mayank here.
Okay. Yeah. Yeah, man. Hello.
Yes, sir. Actually, there was some connection problem.
Okay. Okay. Yeah.
Yes, sir. Good evening. Myself,
Good
Mayank
evening.
Shah, and I'm also pursuing MTech in executives for energy management.
Oh,
And
nice.
I have done my BTech in mechanical engineering earlier.
Okay.
And I have also registered for this course on 7th of August only. So I have missed the 2 weeks, starting 2 weeks.
So, what is your motivation to join this course?
Sir, actually, the work profile for me here in the institute is for the health safety environment. So I'm
Okay.
quite interested in this particular field. So I have chosen this field. So my profile is for the energy and environment only. So that is the
Okay. Yeah.
reason for
Nice.
choosing this course.
Yeah. Yeah. It's actually it's a very good thing that because the person who are working for Bureau of Energy Efficiency are joining this type of course. It's a very good thing so that they can maybe very helpful in making new policies and all. Yeah, it's very good thing. Yeah.
Yes, sir.
Yeah. Anyone else? So I hope you will enjoy the session and maybe this will be very helpful for you. And I request you, like before coming to live session, because in live session we are solving directly problems. Okay. So I expect from you that you have gone through the previous week classes. So I request all, please go through all the videos, all the course content before joining the live session because it will be very helpful for you. Otherwise, you will get bored because you can see that we are directly solving the problems here. So if you know about the week's content, then it's going to be very easy for you, and you will also enjoy participating in the discussion.
Okay, sir.
Yes, sir. We have also seen gone through your videos on YouTube, so it's a good one.
Yeah. Okay. Okay. Yeah. Thank you. So let's come to the question again. So I think we have one option, option B. Anyone else? Anyone else is having any other answer? Let me know. Okay. So let's come with option B. So you are saying option B is correct. Okay. So please highlight your reasoning behind option B.
Sir, option 1 is given is the irreversibility caused to increase the pump work. Okay.
Okay.
Friction is comes, pump work is more.
Yeah,
Irreversibility
correct.
caused to decrease the turbine friction is more. Okay, the turbine work is the less. And the
Okay.
punch point put the restriction of the highest visible temperature. Punch point means difference between the f- heat addition temperature and that converted to water to the steam. One point is there. Okay, differences is there. It's called the punch point. So some restriction minimum is required. If go to
Okay.
more is this problem. And that the temperature to difference is means when you the vapor phase is there. Okay, you
Okay.
want to convert to vapor phase to fully convert it. So the size of the condenser increase, flow of the water also increase.
Okay.
And the fifth is the irreversibility does not occur. It is the wrong.
Okay. Yeah, correct. Correct. Nice. So the correct option is B. And as you said, all the points, your points are correct. So let's discuss it. So the first point is irreversibility cause an increase in pump work, because we know that uh, the pump, because the pump is having some efficiency, some friction is there, some mechanical parts are there. Okay, so there will be various irreversibilities. Okay, so due to that, the pump work, if we go for the like idle reversible, then the pump work should be minimum or maximum. In ideal condition, the pump work, because if we are going for reversible cases, then what about the pump work? It should be minimum or maximum?
Maximum, sir.
Yeah, because the pump work is we are giving some work, we are giving some energy to pump. Okay, so due to the efficiencies, due to the irreversibilities, we have to provide more work. Suppose we want to get the output of 10 kilojoule. To get the output of 10 kilojoule from pump, maybe you need to input 15 kilojoule, because there will be some irreversibilities. So that irreversibilities will account for the 5 kilojoule. Okay, so you have to provide more work, more the reversibility, more the input you will be needed. If the irreversibility will be increased, then maybe you have to input the maybe 18 kilojoule. Okay, maybe 20 kilojoule. So it depend on the efficiencies of pump. So there will be mechanical efficiency. Okay, isentropic efficiency, and some other efficiency will be like depending on like the bearings, also the frictions, like many mechanical parts are there. So it depend on the age of the pump also. Okay, due to those also efficiency will be affected. So you have to take into consideration that. So yeah, option 1 is correct. Irreversibility causes an increase in the pump work. Now, irreversibility causes a decrease in turbine work. So turbine is basically the output work. Okay, is the output work. So suppose if there is no friction, there is everything is reversible. There is nothing. There is no loss in the system. Okay, so we will get suppose 10 kilojoule. But yet we are using some mechanical equipments, so there will be friction. There will be some, the component is having their own efficiencies. Okay, so every part is having their own limitation. So due to this limitation, due to these irreversibilities, we will get only 8 kilojoule, maybe 7 kilojoule. So we are getting less work. Okay, so due to irreversibility, the pump work output is decreasing. So irreversibility causes a decrease in turbine work. The pinch point puts a restriction on the highest achievable temperature. So there is a pinch point. So pinch point basically a minimum temperature difference. Okay, it will be a minimum temperature difference that will be always there. Suppose. So this is suppose if these are the heat transfer diagram. So there is a point, pinch point. So this point will be a point of minimum temperature difference. You cannot go beyond this difference. So it's put the restriction on the highest achievable temperature. So with this, we cannot move beyond that point. So we can go up to that point only. So our heat transfer will be limited. The terminal temperature difference puts point restriction on the lowest achievable temperature. Yeah, the terminal temperature difference is also there. So it's also put some restriction on the lowest achievable temperature. So it depends on the what is the like. Suppose you are having two streams. So your hot stream is maybe at 800 degrees centigrade. Okay, and the cold stream is your maybe at 200 degrees centigrade. So you cannot heat the cold stream up to 800 degrees centigrade. Okay, you cannot go up to the terminal temperature. Okay, because there will be some limitations of the equipments. So yeah, option 4 will be also correct. So the correct and the fifth one is irreversibly does not affect the Rankine cycle. It's directly a wrong statement because we have seen in all first and second option that irreversibility is affecting the pump work, is also affecting the turbine work. So it means that irreversibility is affecting the Rankine cycle. It's affecting the efficiency. So this statement is wrong. So the correct option will be option B only. First, second, third, and fourth. Okay. So let's come to the question number 4. So question number 4 is refer to the TS diagram of Rankine cycle with reheat. So we have given a Rankine cycle with reheat and matched to the following. So we have given a process with some description. So you have to match the process with the description. Okay. So we have given 1, 2, 2, 3, 3, 4, 4, 5, 6, 7 with some description 1, 2, 3, 4, 5. You have to match it. Yeah, please take maybe 3 minutes because it's quite long. Okay. Then we will discuss it.
Option B.
Okay. We will come to the answer. Let's wait for 1 more minute. Anyone else have any answer? We are having one answer, option B. Okay. So we have no other answer. So The one who is saying option B, please discuss your reasoning. Yeah, please let us know your reasoning.
Sir, the process is the 1 to 2 is the high pressure turbine power generation. 2 to 3 is the reheating, and 3 to 4 is the power generation with low turbine. Okay, 4 to 5 is the condensing, and 5 to 6 is the pumping work, and 6 to 1 is the boiling is heating.
Okay. Yeah, nice. So if you remember, yeah, I think, yeah, with this one. So we have discussed at the starting Rankine cycle with reheating. So there is a high pressure turbine, there's a low pressure turbine, there is a condenser, there is a boiler. Okay. So in this way, we are representing this cycle in TS diagram. So the 1 to 2. So this 1 to 2 is the work production in high pressure turbine.
Extension is high pressure turbine.
Yeah. So 1 to 2 option, high expansion in the high pressure turbine. Yeah, this one. So 1 to 2 will go with the 4. Then 2 to 3. So again, you can see the temperature is again increasing 2 to 3. Okay. So it means that we are reheating it. Okay. We are increasing the temperature from 2 to 3 again. So 2 to 3 will be reheating. Then 3 to 4. So again, we are expanding the steam to produce work. It will be in low pressure turbine. So 3 to 4 will be expansion in low pressure turbine. Okay. Then come to the 4 to 5. 4 to 5. So as we have discussed in our previous questions that we are converting the vapor phase to liquid phase. Okay. So 4 to 5 will be cooling of exhaust steam in condenser. We are doing the cooling. Then 5 to 6. 5 to 6 will be pump work, but we are not having 5 to 6 option here. We are having 6 to 7. So 6 to 7 is again, what is this? 6 to 7 is heating of feed water in the economizer. So basically this 6 to 7 is economizer, then there will be boiler. And completely this 1 to 6. 1 to 6 is heat addition, and again this 2 to 3 is again heat addition. So this 3 to 4, this 6 to 7. Okay, but it's mentioned 6 to 1 here. So complete heating. So you can say it's complete heating. So heating of feed water in the economizer. Okay. So the option B is matching with all the statements. So the correct option will be option B. Okay. Is it clear? Anyone having any doubt? Is anyone having any doubt? Okay, I think it's clear to everyone. Am I audible?
Yes, sir.
Okay, thank you. Okay, question number 5. Which one of the following is the correct order of fluid flow in steam power plant? So you have to identify the correct order of fluid flow. Go through all the options.
Option D?
Option
Option D, sir. Option D.
Okay. Option D. We have two answers. Let's wait for another maybe 1 minute. So we have to identify the fluid flow in steam power plant. So we know that
Sir, D.
we have seen, okay, option D, we have another answer, okay. So let's see, the correct answer is D. Yeah, you all are correct. So we know the fluid flow is from, first we are doing some heat addition, then we are expanding it, then through the condenser, then through the pump, and then again heat addition. So it will be, first option A is pump, turbine, so it's wrong. Because after pump, there is heat addition. There is no direct turbine, okay? So option A is wrong. Then steam turbine, pump, no. After steam turbine, there should be a condenser. Option B is also wrong. Then steam turbine, boiler, no. Without boiler, how can you generate the steam? So boiler should be come first. So option C is also wrong. Then economizer, evaporator, superheater. It seems correct. Okay. So option D is correct. I think it's clear to everyone. Any doubt? Okay. The open feed water heater is A. Take 1 minute to answer. Option A, indirect contact heat exchanger, direct contact heat exchanger, neither direct nor indirect contact, or storage type heat exchanger.
Direct type heat exchanger.
Direct contact heat exchanger. Okay, let's wait for a few minutes.
Indirect contact heat
Okay, indirect contact heat exchanger. So we are having two options. Okay, so there going to be a discussion then. Yeah, good. Anyone else?
So it is B. B, direct contact.
Okay, so we have a third answer, direct contact heat exchanger. Okay, so we are having 2 votes for B, 1 vote for A. Anyone else? Okay, let's first start with option A. Yeah, the option A, please explain your reasoning. Option A, indirect
fluid
one-
comes the indirect contact with the fluid because there is a wall in between the two fluids, sir.
okay, okay. So you are just little bit, I think, confused between the direct and indirect. Okay. So option B, do you want to explain? Anyone? Option B.
Sir, it is a kind of shell and tube type heat exchanger where actually that water passes through that particular tubes and the steam extracted from the turbine heats it.
Okay. So that I think that will be then indirect contact. Na? There is no direct contact of the liquids, I think. Because if you are saying that steam is heating inside the tube, cell and tube, then that is direct contact heater. Heat exchanger, yeah.
Yes, sir, that is indirect.
What is the meaning of direct contact, indirect contact? First, we have to, I think, discuss that. What is the meaning of direct contact? Anyone want to tell?
Direct contact is a mixing of
Yeah,
the two
correct.
fluid. Is a direct
It's
contact.
simply
So,
mixing.
there
That
is
heat
a
exchanger in
suppose
direct contact because
there is a stream of fluid A and one stream of fluid B. So A may be at high
Fluids
temperature
are in contact.
and B is at low temperature. So in direct contact, you mean to say both stream A and stream B will mix together. And then there will be stream C. Is it correct?
Yes, sir.
Okay. And in direct contact, stream A is again flowing through some pipes, or stream B is flowing separately. So they are not mixing in between the heat exchangers. After that, there will be some maybe connection to mix those. So for the heat exchanger area, suppose in this area, heat is exchanging. So it means there is no contact between the stream A and stream B in indirect contact. So the meaning of indirect is here that the heat is exchanging actually, because the hot stream is releasing its heat to the cold stream. So hot stream is losing the temperature, the cold stream is gaining the temperature, but there is a no direct contact between them. They are going through their separate pipes, okay, or maybe tubes, or maybe some other mechanism, okay. But in direct contact, suppose this is the area of our concern. So in this area, the heat exchange is taking place. So what is happening here? Both stream A and B are coming here, okay, and they are mixing together, okay. After mixing, there is another stream C. So that is the result of the heat exchange, okay. So they are directly coming in contact, okay. So that is direct contact. So it's the main is mentioned open feed water heater. So basically there are two types of feed water, maybe multiple types of, maybe I think we have discussed two types in the class: open feed water heater and closed feed water heater, okay. So in open feed water heater, there is direct contact of the steam and the condensed liquid, okay. So basically the hot stream and the cold stream will be in direct contact. In closed feed water heater, there will be no direct contact, there will be indirect contact. So they will be passing through either tubes, or maybe one is passing through tube, another is hitting outside the tube. So there is no direct contact. So that is the closed feed water heater. In open feed water heater, there will be direct contact. So the correct option will be option B. Any doubt? Okay. Choose the incorrect statements. So you have to choose the incorrect statements. Those who are new in NPTEL classes, okay, if any question is like this, so it's not necessary that only one answer is correct. More than one options can be correct, okay. So you should remember this in your exam also, in your assignments also, okay. So the motive is that you should know reasoning for every right answer and every wrong answer, okay. So you should understand why the answer is wrong and why the answer is right. So maybe more than one options can be correct. So suppose you are going through the option and you see option A is correct. Okay, you directly mark the option A. That's correct. I think option A is correct, but maybe the option D is also correct. Maybe there are two answers, A and D, but it will be not mentioned sometimes in the question that it's statement or statements. But here is mentioned like incorrect statement, or maybe as is also written there. So maybe more than one answer can be correct, but maybe in some question it will be not mentioned, but yet the option can be, more option can be correct. Go through the options, take 2 minutes, then we will discuss.
Option A and D, sir.
Option A and D. Okay.
D.
Option D.
Option A and D.
Option A and D. Okay.
Option A is wrong, sir.
You mean to say option A is wrong means option A is not an answer? Because the question is
incorrect
proves the
statement, na, sir?
incorrect statement. Yeah, okay.
Yeah.
So you are saying that option A, statement A is incorrect. So it is the correct answer. Am I right?
It can be option B also. Option B.
So I can give you one more minute because we are having multiple options. So let's see.
A and C, sir.
Okay, so I think we should start the discussion. So let's start with option A. So who is in favor with option A? Please explain your reasoning one by one.
Yes, sir.
So who are
Option A is correct.
okay?
Sir, efficiency depend upon the output upon input, na, sir?
Okay,
Okay. So input is increased, feed water heating is maybe output will maybe increase, but you cannot say that ki thermal efficiency will increase.
okay.
And option 2 use the
No, no,
feed
no,
increase
no, no.
the
Please. Let me first be with option A only. I think Mayank was also saying something. Yeah, Mayank, please.
Yes, sir. I was saying that this when we are sending the feed water to the boiler to this boiler feed water pump. So if you are doing the
Okay.
preheating, so
Okay.
that heat energy will be always there with the water firstly. So
Okay.
whatever energy which is required to convert the state from water to steam, that heat energy will be required will be lesser. So the
Lesser.
amount of fuel burn will be lesser.
Correct. So basically, you are saying that we are decreasing the heat input. Yeah.
Yes, sir.
So as we know, the efficiency is output upon input, and if you are decreasing the heat input, then it will improve the efficiency. So the statement A is correct. I think.
Yes, sir.
I think we were having one other answer from A. So I think your doubt is clear now. Because if we are using the feed water heaters, it means that we are using the waste heat in a way that now we need less heat in the boiler to increase the temperature of the water. Okay, because we are extracting the waste heat using feed water heaters. That's why we are decreasing the energy input in this way, because you know the efficiency is output upon input. You are decreasing the input, then output your efficiency will increase. I think option A is clear to everyone. Any doubt? Okay, let's come to the option B. So who are with option B? Please explain your reasoning. Why it is correct, why it is wrong.
Sir, option B looks incorrect.
Means its option statement looks incorrect, means this answer is correct. Yeah, okay. So
Yes.
Why it is incorrect? Why it is incorrect? Why this statement is incorrect? What is the reasoning?
Sir, actually, we are using the same feed water for getting the same output. But what we are using the feed water heater. So that is only going to improve the input efficiency. Sorry, the input energy which we are giving. But the output which we are getting, that will always remain same.
Yeah, correct. So basically, by using feed water, we are not changing the end states of, like you can say, the turbine input state and turbine output state. Okay, so we are not changing those. The turbine input state is suppose 0.1 and turbine output state is 0.2. So we are not changing the 1 and 2. We are doing something extra. So the 1, 2 will remain same and they are still increase in efficiency. So 1, 2 remain same. It means that the output from the turbine is same. Okay, but we are changing the energy input. So this statement should be incorrect because the feed water heater does not increase the work output. It decrease the heat input. Okay, and that's why it's increased the thermal efficiency. But the feed water heater is having no effect on work output. So statement B is incorrect. So for this option, statement B is correct for this question. Now comes to the option C. So what is the reasoning behind option C? Anyone?
So option C is also correct.
Okay, why?
Sir, as we are adding on more feed water heaters, so this will also require more pipelines and more connections to be fitted in the system. And more the liquid have to travel, and there will be more losses involved in the system.
Okay,
This may affect the efficiency of the plant by adding more and more feed water heaters. Maybe, sir. I'm not correct. I can't
okay.
say I'm correct, but maybe.
So first tell me what is the meaning of this incremental increase? What is the meaning of that word?
Means if we compare the two feed water heaters after every stage or in
Okay,
sequence, to the
okay.
rate by which the efficiency increases after the first one.
Yeah, correct, correct. That is the main point. So actually feed waters are increasing the thermal efficiency. But you think that we are adding more and more feed waters, then efficiency will again increasing by the more and more. That is not the case. Okay, so incremental increase. So in if we are increasing the feed water heaters in a like in a row, one by one by one, then there will be decrease in the incremental efficiency. Okay, that is the option is saying, because as the Mang said, as the Mang told that the more and more pipelines, more and more losses will be there. Okay, more and more FH loss will be there. So that's how the incremental increase will decrease. So option C is also, so option statement C is also seems correct, but it's not incorrect. So it's not right answer for this question. Now come to the option D. Any reasoning for option D? I think in option C we have already explained it. So option D is also a correct statement. Okay, so the correct answer will be option B only. So the incorrect statement is only option B. Anyone having any doubt? Okay. So choose the correct statements for reheating in the Rankine cycle. So take 1 or 2 minutes. Option A is it has the benefit of getting high quality steam at the condenser inlet. It always increases
Option C, sir.
efficiency. Okay, option C, it increases work output. None of the above. Let's take 1 more minute, go through all the options. Yeah,
Sir,
any answer?
A and B.
A and B. Okay, nice. We have different options. Anyone else? Please be quick. So we have three options. Option C is correct. Option A is correct. Option B is correct. Anyone else? Okay, let's start with option A. So who is saying it is wrong? Please correct. Please give your reasoning. Who is not with option A? Please explain your reasoning.
So the benefit of using the reheating, so it will take out the moisture content, means the amount quality of steam which we'll get, that will be of the superheated type.
Okay. So option A is correct or incorrect?
It looks correct.
Okay, but I think your statement is not correct. Please read. Please revisit your statement. What are you saying? You are saying that superheated steam. At what? At turbine inlet or condenser inlet?
Turbine inlet.
Turbine
Okay,
inlet.
yes, sir. That is a turbine inlet. Yes, yes.
Yeah. We are asking here is it condenser inlet?
Option B
So
and C, sir.
option.
B and C.
Okay, so then explain your reasoning for option B.
Since in reheating, sir, again the steam is going back to the turbine, low pressure turbine, so the efficiency of the turbine will increase, sir.
It always increase.
The overall plant will increase, sir.
Okay,
It is B, actually B, sir.
B.
Sir, only answer C is correct, sir.
Yeah, please explain your reasoning for answer C.
Sir, we cannot say
Work
the
output is
increase in
increasing means
efficiency
efficiency
because
also increases.
Yeah, please one by one. Yeah, C. Yeah, please explain about C.
sir, work output will be always increase because turbine work we are reheating and we are giving higher pressure turbine and lower pressure turbine. Both work will add. We will get more work than single turbine.
Yeah, nice. Yeah.
And diagram also we are getting more work because we are adding both turbine work.
So you
And
are
for
adding. Yeah.
yes, sir.
So you are adding. You are saying that you are getting more work output. Then efficiency should also increase always. Why you are
No,
saying that
sir,
option B is
because
incorrect?
we have no idea about the heat addition because what amount of heat is added during the heat reheating process.
Yeah. Yeah. Good. So
And sir, option one is also not correct because we cannot say ki higher quality of steam because it comes on the saturation state. So quality improves if it is superheated. So it comes on the saturated or below the saturated steam. So we cannot comment on the high quality of steam we are getting at inlet of the condenser.
okay. That's yeah. You are
Sir,
correct
since
partially. Okay.
B is correct, sir. B is correct because mean temperature of heat addition will increase. So in efficiency also will increase.
Okay. So option B is actually not correct. You are saying that yeah, the mean temperature is increasing. Yeah, we can say that. But in some case, it's because in reheater we can also provide some additional heat from some additional means also to increase the work output. That's why we cannot comment that it always increase efficiency. Suppose you are not, because it is not mentioned clearly, it's only giving the reheating. Okay, you are not having the complete diagram with you. You are not having every states points. Okay, so directly you cannot say that it will always increase the efficiency because you have to consider the the soul of the question. So it's saying the reheating, okay, it always. So always means always. But if you are increasing the reheating by some external means, okay, you are reheating, you are doing the reheating, but I am using some external heating, then maybe the heating will also add to your heat input, okay, and maybe that is not you think that you are getting more work output, that's okay, but the heat addition is also quite more. So sometime it will not increase the efficiency. So it cannot be case B. Option C, it increase work output. Yeah, correct. Because if you are doing reheating, then work output will increase for sure. Okay. Now come to the option
Okay,
A.
sir.
Option A. I think everyone is know the answer, but they are just confused about the high quality steam. So they are confusing that high quality steam is only steam or superheated steam, but that is not the case. So let me draw a simple diagram. Suppose this is point 1. Okay. So it is without reheating. So if I use the turbine, so expansion, suppose I am using the idle, so it will come here. So suppose this point A. Now I am doing some reheating. Then what will happen? Sorry. Let me just redraw it. Suppose this is the point A. Okay. So I'm directly coming to the expansion. So this is the point we are getting. So if I'm not doing reheating, so I'm coming to point 1 to point 2. Now, if I am doing reheating, then what is happening? I'm expanding it here, then again reheating, then I'm coming to point 3. I'm again doing reheating, and I'm coming to point 4. So what is happening here? 2, 3, 4. So suppose the X will be here. What will be here? X, suppose any quantity. It's 0.6, maybe 0.7. Let's 0.7. Then what will be the X at 0.3? Is it more than 0.7 or more less than 0.7?
More than 0.7.
Maybe it will be 0.85. And what will be the X at 0.4? It is just at the
1.
saturation curve, 1. So what is happening here? If you are reheating, what is happening here? What is the change in the X? Is it increasing?
Increasing.
So the dryness fraction is increasing. What is the mean of dryness fraction then?
Dryness fraction means the vapors divided by water quantity.
Yeah, it means basically dryness fraction is saying the quality of steam, na?
Yes, sir.
Yeah. So that's why it is benefit of getting high quality steam at the condenser inlet. Okay. So if you are here, so you get the steam with 0.7 dryness fraction only, as compared to 0.4 or 0.85. So if we are using the reheating, we are increasing the steam quality so that there will be more part of vapor than the moisture. Okay. Why? If the very less liquid part is there, then what will so the component will be in safe limit. Okay. So basically, the reheating is increasing the high quality of steam. So correct options will be A and C. For those who are having doubt with the option B, I request you to please refer the some reference book or also class notes, so you will get your doubt clear in more comprehensive way.
Sir,
Okay.
one question is there.
Yeah, please.
Sir, is the option A, it has the benefit of getting the high quality of steam at the condenser inlet. If
Yeah.
the condenser inlet giving the high quality of steam,
Mhm.
so we require the more water for the cooling.
Okay. Yeah.
Cooling water, we need the one the pumps is there.
No, why will you require more water to cooling?
Because of the internal this energy is the more not the
Okay.
vapor energy is more.
Suppose yeah. If water is required, water is more, then what is happening here? So what the concern?
Concern is the more work given for the cooling, because we need the pumps for the cooling,
No.
na?
No. You are not. I think you are confused, maybe. So actually, you are saying that we have to pump more. Okay. Am I correct?
Yes, sir.
Yeah. Okay. Yeah. Actually, the Rankine cycle is open cycle or closed cycle?
Is a
Just tell
closed
me
cycle.
that thing. Rankine cycle is closed cycle. So suppose if there is this Rankine cycle is completely closed cycle, so do you think that the quantity of water will change? It will increase or decrease, do you think?
Pardon, sir?
You are saying that Rankine cycle is a closed cycle and the fluid
Okay,
here
sir.
is water. Okay, we are considering it a closed cycle. So do
Okay,
you think that the quantity of any fluid in any closed cycle will increase or decrease? What do you think?
I'm not saying about that working fluid. I'm saying that the condenser fluid, but using the cooling.
Okay, but yeah, okay. You are okay. So you are saying that the fluid which we are using for the cooling, that
Yeah.
will be required more.
Hmm.
Yeah. Okay. So tell me one thing. Are we considering this liquid in our efficiency calculation? Are we considering anywhere like this is the diagram of Rankine cycle? So if you are calculating any efficiency, are you considering this 4 to 5 anywhere? Heat rejection
No,
part?
sir. No.
Basically, we are focusing on
No.
our
Rankine cycle.
work output and our heat input. We are not focusing about the heat rejection. Why so? What is the reason of that? Suppose this point is 4 is near here. Okay, you are saying that suppose this point 4 is here. So you are saying there will be
Okay.
less requirement of the water. But you should consider that this point 4, okay, is at steam. Okay, we are converting into water. Okay, so what is the temperature of this water? What is the temperature of point 4? Just suppose any temperature. What is the temperature at point 4 days? What will be the temperature? Any idea?
Is equal to 4.
No, is it equal to 4? But what is the supposed temperature? What is the value of temperature? I'm asking that.
Is just 75 degrees.
Okay, 75 degrees.
No, sir. Just
Sir,
Any-
it is
anyone
100
else?
degrees, sir. 100 degrees, sir.
Yeah. Maybe more than 100 degree, little bit. Maybe some moisture is there. We cannot say completely. Yeah, but near 100 degree.
near.
Okay.
Okay.
So
Yes, sir.
if you are cooling that water to liquid at suppose 100 degree at same temperature, so you are basically you are supplying the cold fluid. Okay, cold water. Okay. So do we need to input some heat for getting the cold water? Because cold water is freely available. Water at room temperature is easily available. Okay, we are not considering the cooling water required in our condenser, because that is at room temperature, that is easily available. We are not considering that. We are this pump work, because at last we are coming to point 5. We are considering the pump work of the working fluid, the pumping required for the working fluid. And suppose you are at 4, then obvious the work output is more. Okay, and also your equipment will be remain in safe limit, because there will be less moisture content in your working fluid. Okay, So that's why we try to make the condenser inlet near the saturation curve. Okay. So we are not focusing on the condenser, like cooling liquid for condenser, because that can be easily available. We don't have to input more energy for that. I think your doubt is clear now. Is it
Yes, sir.
clear?
Yes, sir.
Sir,
Okay,
I have
thank you.
one doubt, sir.
Yeah, please.
Sir, I have doubt with option A.
Okay, option A. Yeah. How?
Sir, there is a dryness fraction if we are considering, then saturation curve will be parallel to the dryness fraction if we are considering it
Okay.
everywhere, because saturation if we are जो turbine outlet will come near the saturation curve.
Okay.
So dryness fraction will be more. We are not sure, sir.
No, you are not getting the point. Let me again. Suppose.
Because sir, 0.7 for the more temperature. If we are considering temperature, if we are not reheating, then
So these are the
adiabatic
lines
line
of.
will come above the curve.
Yeah, I think these are the lines for dryness fraction. I think you are
Yes, sir.
getting
Yes,
this.
sir. Yes, sir. Yes,
Okay.
bilkul.
So if you are doing the reheating, okay, in one case, suppose your point is at 1. Okay. So
Yes,
you are
sir.
not doing any reheating. Then what will happen? Maybe you are coming up to this point.
Yes, sir.
Okay.
Maybe this curve may be the same 0.7.
Okay. Let me. Yeah. Now you are doing some reheating.
Yes, sir.
Then where we are coming?
Here,
So what is
this
happening?
point.
The dryness stress is increasing or decreasing?
Sure.
If you are again reheating, you are coming at the saturation curve. What is happening here? You can see now. So the dryness fraction will increase. You can say
Okay,
directly. Okay.
Means
Dryness
condenser
fraction.
inlet temperature is okay. Okay, thank you.
Okay. We are looking at the condenser inlet temperature. So
Yes,
we
sir.
tried so that there will be
Yes.
less moisture at the
Yes, sir.
Inlet.
yeah.
I understood.
Okay. Yeah. Anyone else? And anyone else? Anyone have any idea why the moisture is like we are focusing so much on the moisture? Suppose the condenser,
Yeah, because
as you let me complete. As we are already converting the steam into liquid in the condenser, then why the quality of steam is important at condenser inlet? Anyone want to focus on that? Why we are focusing about the condenser inlet, quality of steam at condenser inlet? I am saying again and again that there should be less moisture at condenser inlet. Why so? What is the reason?
Yes, sir, because the condenser itself is a kind of heat exchanger. So we have
Okay.
to maintain some temperature difference between the incoming cooling liquid, like it is a seawater or whatever water it is, cooling water, and the incoming steam. So there must be some temperature difference so that because of that difference, the heat transfer should take place.
I don't think so, because in condenser we are converting it to completely liquid. So suppose at the condenser inlet there is less moisture, but what will be that condenser outlet? That is completely liquid. So what is the reason behind less moisture at condenser inlet? You are getting my point. That is you are saying that is correct in that manner, but I am asking why the quality of steam is important at condenser inlet. Why we are focusing on that part? Because in condenser, at last what is happening? Suppose condenser is 10-meter long. So the starting point at 0 meter, there is no moisture. But what will be there at the end of the condenser? There will be completely liquid. So basically the 10-meter is having some part of liquid, some part of moisture. Only a particular point there will be steam. After that, again, suppose the dryness fraction 0.9. So mean there is moisture. 0.8 there is moisture. So the complete condenser is having some moistures, and also we are flowing cold water outside also. So there is also water. So why the condenser inlet steam quality is important? It's a very good point. Yeah, anyone wants to address it?
Sir, due to avoiding the corrosion problem in the tube, turbine outlet.
Yes, that's what I want to hear it. Yeah, turbine outlet. Actually, we are not focusing on condenser inlet. We are focusing on turbine outlet actually. But we are saying is that
Yes, yes.
condenser inlet. Because if the turbine there is a moisture, then what will happen? That moisture particles will damage the turbine blades. Okay, because turbine blades are rotating at very high RPM, and if some water bubbles are there, then the water bubbles will strike the turbine blades. Okay, and in some manner, and you can see the complete detail on some reference book. So that can damage the turbine blades.
Yes,
So
sir. It
we
will
are
cause the pitting and corrosion.
pitting
Yes.
and corrosion. Yeah. So that is the point. So turbine blades will be get damaged. So we are focused on turbine outlet, but we are saying it condenser inlet. Okay, because the condenser inlet is the point of turbine outlet. I think now it's clear to everyone.
Yes, yes.
Yeah. Okay. So a quick numerical. Okay. So given below is a Rankine cycle with reheat. The table below gives the properties of the working fluid at important points. 0.5 correspond to a saturated liquid coming out of the condenser at 10 kilopascal. Steam enters at high pressure turbine at 15 megapascal. The specific volume of saturated liquid at 10 kilopascal is 0.00101 meter cube per kg. We have given some data. So what will be the pump work? Take 2-3 minutes and try to answer. Always remember, very careful with the units. Okay, because we are having some units in kilopascal, some in megapascal. Okay, always very careful with the units. Also, we are having enthalpy in kilojoule. Units are very important whenever you're solving. Because in options also you can see the option A is 15.139 and option B is 151.39. So there is only difference of a digit. And similarly option C and D also. So units are very important. Yeah. Anyone?
Option A.
Option A. Okay. Just wait for 1 more minute. Okay. So let's see the solution. So yeah, option A is correct. The correct option is option A. So the pump work, what is the pump work? Pump work will be the V5 into P6 minus P5. The pressure at 0.6 to 0.5, difference between the pressure at 0.6 to 0.5, and the specific volume of the fluid. Okay. So V5, so we have given VF at a 10 kilopascal. Okay. So we have given in the questions saturated liquid is it 0.00101 meter cube per kg. So WP will be V5 into P6 minus P5. We have given the pressures. So put in kilopascal, you will get answer in kilojoule per kg. Okay. For detailed numericals on Rankine cycles, you can refer the class videos. I think professors have solved a very good numericals in class also. Anyone having any doubt? Okay. One important thing is there because sometimes many students got confused with the steam. This table actually they will see various points are there. Okay, so don't confuse with it. They are asking only the pump work. Okay, so you have to only focus on point 5 and 6. Don't bother about the table. You don't need it. Okay, you just only need for the point 5 and 6. So only see the relevant data, only find the relevant data and start solving. Don't think about the other things. Okay. Any doubt? Okay. So consider the problem 6. What will the total heat supplied? Now again, the same question. I think the same question. Let me wait a moment. Yeah, same. So now you have to find out the same numerical. Just find out the total heat supplied. Okay, what will be the total heat supplied in this question? Just find out. Now you have to use the table because now you have to focus on which points. Anyone? These are the options. These are the data. Anyone is having any answer? Okay. So what will be the heat supplied? So we can see the heat supplied in boiler and reheater. So boiler will be 0.5 1 to 6 and reader will be 0.3 to 2. So you need enthalpy at 0.1 H1 and H6 and H3 and H2. So the heat supplied will be H1 minus H6 plus H3 minus H2. So we have given, I think, enthalpy of state 1, 2, and 3 we have given. Okay, we can see that enthalpy of state 6 is not given. So we have to find that. So for enthalpy of 6, first we need to find the enthalpy of 0.5. So enthalpy of 0.5 plus we can add the work of pump. So we can get enthalpy of 0.6. So enthalpy of 0.5 can be found out from the curve because we know that 0.5 is at saturation point. So the H5 is a specific volume of the saturated liquid at the condenser outlet. So it will be H5 enthalpy of the liquid at 10 kilopascal. It will be 191.81 kilojoule per kg. And we know the work done. Okay, we have given HF. So for H4, we have given HF, but H5, we know that it's at the point at the curve. So the H5 will be HF of 0.4 that we have given here. So it will be 191.81 plus the pump work. So it will be 206.949. Okay, so now we have H6, we have H1, H3, and H2 already. So the heat addition will be H1 minus H6 plus H3 minus H2. That will come to 3896.051 kilojoule per kg. So the correct answer is option B. Anyone is having any doubt? Anyone having any doubt? Okay, I think there is no doubt. Am I audible?
Yes, sir.
Okay, okay. So question number 11, again consider the same problem. What will be the thermal efficiency of the cycle? So again, you have to consider the same problem. Now you have to find out the thermal efficiency. So I think you have found out the heat addition. For thermal efficiency, you need to find out the work output. So I think you need to consider the point 1, 2, 3, 4. Find out the work output from this data. I think after work output, you can find out the efficiency. You know the pump work, you know the heat addition. Take 2 minutes to solve. Because this one question is having 3 questions, okay? With the same data, we can solve 3 questions. So it's good to practice these type of questions because you have to aware about these types of questions.
Option, sir. 55% approx.
Options are 22%,
Is a
4.5,
45%, sir.
and C
45%.
45 and D 2.2. Okay, let's wait for one more minute.
45%, sir.
Okay, nice. Let's wait for one more minute. Any answer? Okay, we have an answer. So let's see the solution. So thermal efficiency is what is the net work output upon total heat supplied. So we have computed the total heat supplied in the problem, last problem. Okay, so heat supplied is 3896.051 kilojoule per kg. So we have heat supplied. Now the net work output. So the work output will be the output from 1 to 2 plus 3 to 4 minus the pump work 6 to 5. So it will be WT1 high pressure turbine plus WT2 low pressure turbine minus pump work. Okay. So where WT1 and WT2 are work output of the high pressure and low pressure turbines respectively, WP is the pump work. So W net will be H1 minus H2 plus H3 minus H4 minus WP. So enthalpy at H4 will be, you have to find out like this: HF at 10 kilopascal plus X4 the friction, and then HFG. So we will get the enthalpy at 2335.1361. Then W net will be H1 minus H2 plus H3 minus H4 minus WP. It will be 1767.87. So you have the net work output, you know the total heat supplied. So the answer will be 1767.87 upon 3896.051 comes to be 45%. Okay. Yeah. Come to the next question. So in an adiabatic turbine, the steam expands steadily. The data is given in the figure. What is the power output of turbine in kilojoule per kg? Note the inlet and outlet of turbine are at same datum. So you have to, same datum means you have to consider the potential energy as 0.
Option B.
Option B. Okay, let's wait for a little bit more. Okay, let's see the answer. So we have to first write the steady flow energy equations for expansion through the adiabatic turbine. That will be the H1 plus V1 square by 2. We have to consider the kinetic energy because we have given the velocity at inlet and outlet and the enthalpy and the work output. Okay, so W out plus adiabatic, so there is no heat loss, so the Q will be 0. So put the steady state equation, you have all the data. So W out will be H1 minus H2 plus V1 square minus V2 square upon 2. Answer will be 859 kilojoule per kg. So the correct answer is option B. Is it clear? Okay, I think it's clear to everyone. Question number 13. The figure below shows the TS diagram of a steam power plant. Based on a Rankine cycle, find out the bake work ratio. We have given state points, specific enthalpy points. You have to find out the bake work ratio.
What is back work ratio, sir?
Okay, is it not covered in the class? Okay, maybe it is not covered. Maybe it will be in the reference book. So let's see. The bake work ratio is that work ratio of the pump work and turbine work. Okay, so the bake work ratio is given by the pump work and turbine work. So pump work will be H4 minus H3 and turbine work will be H1 minus H2. So you know the all the enthalpy at points. Just you have to put the data in this formula. So the bake work ratio is 0.019. So our aim should be the bake work ratio should be lower or higher. What
Sir,
is our motive?
is lower.
Lower, yeah, because we require more turbine work than and very less pump work. Okay, we'll come to the question number 14. So in a power plant, the steam enters and leaves an adiabatic turbine steadily with specific enthalpies. Okay, if the expansion would have been isentropic, then steam would have the turbine with specific enthalpy. Find out the isentropic efficiency of the turbine. So you have given some data regarding the turbine. So calculate the isentropic efficiency. I think these are the numericals. So that's why I was telling you, try to cover all the previous week classes before this live session, okay? Because it will be more helpful for you to solve the question, okay? And to ask the doubts also. So basically, isentropic efficiency means in actual, we know that turbine work will be lesser, okay, than the isentropic work. So I mean there is an efficiency. You have to find out that. So you should first know the efficiency formula for the isentropic turbine, and you have the points. Okay, let's see. So the efficiency of turbine is written as, suppose this is the turbine work from 1 to 2s. So 1 to 2s will be the isentropic work, and 1 to 2a will be the actual work. So the actual work will be lesser than the maximum work. So the turbine isentropic efficiency will be the actual work upon isentropic work. So H1 minus H2A, this 2A point will be the actual point. So H1 minus H2A upon H1 minus H2S. Okay, so you have all the data. So put the data and you will get 91%. Okay, is it clear? Okay. So the last question for today's class. A steam power plant operates on idle regenerative Rankine cycle with open feed water heater. Steam entry a turbine is set at 10 megapascal. Okay. And 600 centigrade and condensed in the condenser at a pressure of 5 kilopascal. So we have given all the data. So it's quite long. I think it will take time. So maybe we can directly see the solution because we are about our because the class time is about to end. So let's see the solution. So we have to, because we have given, you can see we are using some steam extraction at some points. Okay, as we are extracting steam at point 2. Suppose the M1 quantity was coming here, so maybe M2 is going here. Okay, then remaining quantity is coming to the 3 to 4. So we have to consider those all things and you have to calculate the data. So let us assume M is the fraction of steam bled at state point 6. Now apply energy balance to feed water heater. So MH2 plus 1 minus MH5 equals to 1 dot H6. So we have to apply the energy balance equation at feed water heater. Based on that, we can find out the value of M. So we from table we can get value of H2, H6. Okay, H5 can we can calculate from this formula. H4 plus WP1. Okay, where Pi is the pump work for the first pump 4 to 5. Then again you can calculate it. So the H5 will be this. So the equation can put it here. So M will be 0.2423. Okay. Yeah. So 0.2423. So my advice is that because sometimes these questions are quite big, actually. Yeah. So maybe when you read it first, so it's like it's a quite big question. Okay. But we are only asking a one point, determine the fraction of steam extracted. So focus on that only. So you have to focus on that part only, and you have to identify which points are important, which state points are important for your respective question. Okay. So don't have any fear from this large question because you will see the table, you will see the diagram, so you will get some fear in you and maybe your confidence will get loose. So don't do that. Okay. Try to focus on the question, read it carefully, focus on what is the exact question, what are they asking. Okay. So focus on those points only. Start with the basics. If you are having feed water heater, apply the energy balance. So you have applied the energy balance. So from energy balance, you can see you require the enthalpy of state point 2, 5, and 6. So for 2 and 6, you are having enthalpy, but for 5, you need to calculate. So how can you calculate the enthalpy of state 5? So you know the enthalpy of state 4. If you know the work, okay, then you can calculate the enthalpy of state point 5. So enthalpy of 4 plus the pump work. So for pump work, you are having the specific volume, the pump that is handling liquid. Okay, you know the pressures at the end points of the pump. So you can calculate the pump work by multiplying it. Okay, so V4 into P5 minus P4. So you know the pump work 1.2 kilojoule per kg. So therefore, the actual enthalpy of H5 will be H4 plus the pump work. It's very slight, only 1.2 kilojoule, but it can make a difference if you are calculating up to 4 digits. Okay. In our earlier question, I think we have discussed one question that we can neglect the pump work. So it's very small, 1.2 kg. So sometimes we can neglect it. Okay. But if it is given in the question, only then. It is not given, then we have to consider it. So now you get the enthalpy of H5. So you can get the mass fraction putting this formula. So initially, I think it was quite big. It was seeming very difficult, but from a solution, it seems very easy. I think, is it clear to everyone? Is it clear to everyone? Okay. Okay, I think it's clear. So our class is about to end. So I hope you enjoy the session. Okay, there is one important announcement. The next class will not be on the Friday actually, because I have some other work. So the next session will be going to held on 22nd August. Okay. So the link for that will be shared on you on the course website and on your mail also. So it means that there will be no session on next Friday. So on 18th of this month, there will be no session. So the next session will be on 22. For week 4, there will be a session on 22 and again on 25. So from next week, we are not having any session. After that week, we are having 2 sessions in that week on 22nd and 25. Okay. And for the same announcement, you will receive the mail also and the link also. Okay. And the PPT and the video of the session will be shared with you. So don't worry, you will get everything. So I hope you have enjoyed the session. So now I would like to end the recording and end the session. Okay, thank you everyone. Thank you for joining. I hope you will join in next session also. So we will have a great discussion. Any feedback? Anyone want to share any feedback? Because I think there were 2 new students today. So if they want to share any feedback. Okay. Okay. Thank you for joining. Bye bye.
Thank you, sir.
Thank you.
Yes, sir.